Good morning, everybody. Welcome back to the Wonderful World of Physics. I'd like to start off things today with just a little checkup on how you feel you're doing so far in grade 12 physics. Grab your multiple choice letters. Face down when you're ready. The eyes to the front, please don't look around. And hold them up. Hold them up. Keep them up for a little bit. Thank you very much. So I saw quite a variety of answers across the spectrum here. I was pleased to see quite a few A's and B's, but also a significant number of C's, D's, and E's. If you're in this category, in the category where you really want to make an improvement, please make sure you come and talk to me so I can give you hints and suggestions on what to do. And also keep in mind that there is no magic bullet or quick fix. The only real solution to make a genuine improvement in how you do in something that is challenging is a long-term commitment of hard work with regular feedback. Later on in today's class, I will be giving back your test. Overall, the results were quite good. So many people, I think, are in this category. But if you still find yourself down here, it's very important that you come and talk with me and we figure out what we can do to help you out for the next part of our grade 12 physics course. Okay? Now, to start off today, I would like to take a look at a concept question. So please take a moment, no discussion. Place your cards face down when you're ready. Okay, eyes to the front, please, no looking around, and hold them up. Hold them up. Okay, face down, please. Don't share your answers yet. Now, please remember that what makes this a valuable learning process is that you only reveal your answer when it's your turn to talk. And when you share your answer, please explain your reason why, or explain why you agree with the person who spoke before, or why you disagree. And we'll go in the order of pink, blue, white. Go.
Oh no, you're subbed at 10. Oh wow.
Please choose your answer. And eyes to the front. Please no looking around. Eyes to the front. Hold them up. Let's see. Let's see. Thank you very much. Okay, very good. Overall, the class score went from probably a bit less than 50% correct to 100% correct, which was excellent. The correct answer was D, and a quick explanation. Why was D correct?
Because velocity is not something
And
Okay, because since it's sliding down at a constant speed, that means no external net force is acted upon the rock. So that means that there was no net force acting upon it, so that it couldn't have been any of those.
Great, great. Okay, very good, very good. So just getting us thinking about our forces on an incline there, which we were looking at last class. And now in today's class, we want to take a look at another very important part of our understanding of forces, that of interactions. We have been talking about interactions since we started our force unit, but today we want to focus on this idea. Now, our understanding of interactions comes from Newton's third law, and today's investigation will be both a refresher of what you learned in grade 11 about Newton's third law, as well as an opportunity to extend and deepen your understanding. Ladies and gentlemen, please open your handbook to page 47. Choose your role and adjust your seating. And get started. Ladies and gentlemen, we're going to do a quick check-in on your work. On your big whiteboards, I would like you to draw that first interaction diagram and force diagram, then put it up against the wall and window so that it cannot be seen. Ladies and gentlemen, what we're going to do is a quick version of our whiteboard walk around. I'm just going to have you flip your whiteboards over so that everybody can see them, but then just sit back down with your group and take a quick look around and decide if there's any improvements you can make to your work. So flip it over, have a seat, and look around.
The middle. Well, all of them I could.
Now let's just do a quick check on our diagrams. So when you draw your interaction diagram, you should only be writing words for the names of the objects that are interacting. In this case, how many objects are interacting? Three objects are interacting: the book, the table, and the earth. Good. How many interactions are there? There are two interactions, and the only symbols that you should have is the symbol for a single letter naming the interaction. Okay? These diagrams are not describing forces yet, so we don't use the symbol F. But what I do want you to keep in mind is that when we see this kind of diagram, that single line, that line from the table to the book labeled N, tells us there is a normal force interaction between the two objects, and that this interaction has two parts: a force of the book on the table and a force of the table on the book. But that one single line represents all of those ideas. Okay, so please make adjustments to your own interaction diagrams. The force diagrams are looking great. Please keep going. Hey guys, how's it going?
Okay.
Good, good. I was wondering about our two forces here. Are these forces the two forces of a single third law pair? Why do you think that?
Because they don't follow all of these characteristics.
So which characteristics don't they have?
Not the same type.
Not the same type? Any others?
They don't involve the same characteristics.
Good, good. But a lot of people would say, yeah, they have to be a third law pair. Look, they're the same size in opposite directions. Why are they the same size?
Because objects at rest have that in the y direction.
And if the objects are at rest, the forces must
Cancel out. Equal to zero.
balance. Okay, good. Good.
They are called they are balanced, right? But they must act, the third law pair must act upon two objects.
你给它勾出一遍什么是 third law pair?
Third law pair must involve
Yeah.
same pair of objects,
Yeah. So basically,
which means two objects.
normal force, the force that in the second third law pair is the normal force that from book to table. The pressure.
Table to book, book to table.
So are these two forces part of the same third law pair?
Pardon?
No hard.
Are these two forces a third law pair? Because
Because first law
They
is
are acting on the same object. Book. They are okay.
now, why are they the same size? Because that tricks some people into thinking that they're a third law pair.
the book is rest, and which means the force are balanced, and that force is equal to zero. Or based on the gravitational force is constant, as the mass of the book is constant, and 9.8 we all know that. So basically, to balance that, we get a normal force that is constant.
Good, good. So it's at rest, and according to the first law, we know that the forces must be balanced. Okay, very good. Hello, how's it going? Good. You've drawn two forces on your force diagram. Are these two forces part of a third law pair?
No,
Why is that?
because
Okay, we don't think so because
Yep.
on the top it says that for a third law pair, that to be the same pair of objects.
Uh-huh.
So for the two forces, the normal forces between table and book, and the gravity is between Earth and book. So we think it might not be the same pair.
No,
It shouldn't be
I'm thinking this
the
because it's
third law pair.
So they're different pairs of objects. Is there an additional reason why?
They're not the same type.
No, yeah, you're right.
Good, good. But we do notice that they are the same size. Why is that?
The book is at rest, meaning the force should balance each other. That's why they have same.
According to Newton's first law. First law. Okay, very good. Very good. Hey guys, want to check in with you about your forces here. What has your group decided? Are these two forces part of the same third law pair?
No, because they're not the same pair.
They're not the same type.
They're not the same type? So one of them is... Good, good. Now we do notice that they are the same magnitude, and that kind of tricks people. So why are they the same magnitude?
Because it's at rest and there's only two forces acting on it.
Opposite direction. So balance out each other.
If normal force were to be reduced, you can reduce normal force, but gravity will remain the same.
Okay, very good. Very good. How's it going? Good, good. Question about your two forces here. Are these two forces part of the same third law pair? What did your group decide? Who's our speaker today? Eva? Yep.
They're not.
Uh-huh.
They're not the same type of force, and they also don't act on the same pair.
Good, good. But they look deceiving because they have the same magnitude. So why do they have the same magnitude? Sorry, because there's no...
motion.
The object is at rest, and that means
the forces are equal.
the forces must be balanced. Very good. Good. Keep going. So what is the size of the force of gravity of the book on the Earth?
The same as the size of force of the Earth on the book.
So if the Earth was exerting a 3 Newton force on the book,
It would also based on a 3 Newton force on the Earth.
So the question is, why does that 3 Newton force not appear on this force diagram?
Because the Earth's mass is so much larger than the television affected very small amounts.
So the Earth's mass is very large, and that means that with that small force acting on it, something else is going to be very, very small. So that's the physics word we want to use here. The acceleration of the Earth is very, very small. Now, we're not thinking about acceleration, or we're not trying to picture the acceleration with our force diagram. We're just picturing the forces themselves. And that force is the same size as this force that you've drawn here. So why is it not appearing on this force diagram?
Because we're not talking about the Earth as a system, we're talking about the Earth as a system.
So our choice of system is the book.
And however the Earth moves doesn't really affect the book.
So this force diagram is only showing the forces acting on, only acting on the book. Now we could choose a different system, and that force would appear. What system would that be? So if the Earth was the system, then that force would appear. Okay?
So we shouldn't necessarily say it's insignificant. We can say that the system is the book, so that force would not appear.
Correct. Yeah. Very good.
Would we have to have like another line?
Oh, then
That's bio.
yeah. Oh wait, I like to. Okay, wait, but then so there'd be 2 downward forces, right?
Well, wouldn't there's 2 down and then physics? Is that right? Yes, for the.
The bio and physics is
Yes, I'm talking about the physics on bio.
and then everything else. Okay.
Wait, but then we don't need to include.
Being added on to Fn, or Fn is being added on to Fg.
The order in which you draw them isn't important. Just make sure you're drawing them tip to tail, so we can see how they're adding up in the vertical direction. Okay?
I said the force of gravity is acting downwards. Oh, wait, okay, never mind. Yeah. But I said it was acting. I don't know why I said it was acting.
With our interaction diagram, does this show the direction of anything? No, it's just showing some basic ideas. So, which are your objects that are interacting in this situation?
The 2 books.
Uh-huh. Good. So you should just have 4 words only in your interaction diagram. Okay? And then think of how to draw those interaction lines between those objects. Okay? Because you're very close. You're very close.
No, but the force of gravity is
It's this here, and this is going to be force, because here's our force of gravity.
But then you don't know if it's a bio.
I don't think.
Ladies and gentlemen, many groups are taking a look at the interaction diagram for the 2 textbook example. When you draw your interaction diagrams, the only words that should appear are the names of the objects that are interacting, and those names should only appear once. So use that as a help, as a hint for how to construct those diagrams. Please keep going. How are you guys doing? You okay?
Yeah.
Yep. Hey guys. Let's take a minute to look at your force diagram for the physics book. So, which one of those is the physics book? This one here. Okay. Now, if we look at your interaction diagram here, how many interactions does the physics book make with the external objects? So it interacts with the earth, with the table, and... So how many interactions in total for the physics book?
3.
So how many force vectors should appear on that force diagram?
3.
Correct. So there's a force vector that's missing right now. Which one is it?
The biology and physics.
Okay. And if we take a quick look at your biology force diagram, how many interactions does the biology book experience? 2. And let's do a double check. How many force vectors do you have on that diagram?
2.
So that sounds okay. All right. So you'll need to add in another force vector and then think very carefully about the size of those vectors. All right. Is that okay, Chris? Yeah. Good.
Change, but it's not shown in here.
Sorry, say that again?
Even though we know the force of gravity changed because the mass increased.
The mass of which object increased?
The mass of these...
No, listen. The mass of the physics book didn't change, did it?
No, but there's mass added.
Since there's two systems, you don't have to gravity that change.
Nothing happens.
Well, the normal force from the table changed, like you said before. But the gravitational force.
So it's very helpful to keep it clear in your mind, the mass of the system that you're talking about. So if it's your physics textbook, does the mass of the physics textbook change? No, but there's a new force that's added onto it when you place the biology book on top. Okay? Good. Hey guys, could I ask your group to draw these two force diagrams on a big whiteboard, and then in a couple of minutes I'll have you explain that to the class?
Okay, sure.
So think very carefully about the size of the force vectors. Okay? Good. Hi there. Let's talk for a moment about the force diagram you've drawn for the biology book. Our interaction diagram helps us to construct these force diagrams. So if we take a look at the interaction diagrams, how many objects are interacting with the biology book? So which objects are they? The physics book and... So how many force vectors should appear on the force diagram? Okay. Let's pause for a moment here, and I have one group which is going to explain their force diagrams for this 2 textbook situation. So please hold the whiteboard up nice and high so everybody can see, and adjust yourself so you can listen carefully to their descriptions. Okay, take it away.
Bio textbook, physics textbook. We'll start with the bio textbook. It's pretty simple. So the force acting on the normal force acting of the physics textbook on the bio textbook is equal to the force of gravity pushing the bio textbook down. So that's why those two are equal. Over here, the physics textbook is interacting with the table and the bio textbook. So the table is pushing up the physics textbook with the same force, the same total force pushing down on it. And that force pushing down is made up of the force of gravity acting on the physics textbook and the normal force acting on the physics textbook from the bio textbook. So this whole thing is equal to that. And then just the force of the bio textbook acting on the physics textbook is the same as the force of the physics textbook on the bio textbook. So those two lines are the same, and that's the force pair. And yeah, this is the smallest force because the physics textbook has a smaller mass.
Okay, do we have any questions about the way the forces are drawn there, or how we've decided this? Now, one thing that I would like you to do, if we add on these little X's to show our force pairs, I didn't explain it well in the handbook, just draw the X to the side a little bit, just so it doesn't add any confusion to the force diagrams. Okay, thank you very much. Please keep going.
Are they like exerting a force of magnetism on each other, like on top of normal force?
That's their shtick. That's what the magnets do.
So both of them.
So there is a magnetic interaction between these two objects,
Which causes a normal force?
and it's an attractive interaction.
But does that cause a normal force, or can you say that the force is actually magnetism?
So we need to
Because
think
they're in
about...
contact, you could say it's a normal force caused by the attraction between them. But
So, how many interactions are there between the two magnets?
Two.
One of them is?
Normal.
The other?
Magnet.
That's right. Good. Just like with the Earth, you can have two types of interactions with it right now. Such as? Okay, good.